and circuits for very high power applications. He is also an adjunct professor of Semiconductor Division with Linköping University. Earlier, he has also served as a distinguished lecturer of IEEE from 2014 to 2021. And he is also an IET fellow since 2010. Mohammed, thank you so much. Would you need a microphone, I believe?
I think I will try my best to.
So if you're able to listen to him
Okay, with this sound quality, I should say yes.
Perhaps not. Okay.
Is it okay?
The last bench says no.
I will try my best to speak a bit louder. I am louder by default like this. Hello?
But then you can just plug it in.
I think I will try to.
Okay.
But okay, see, I think the title of my talk is already shown here. So some of these slides, the earlier part of my presentation, were shown by Ali Raza and other speakers. So my life is a little more simple now because the visions and trends of power electronics and such these have been fairly understood and have been shown by Ali and previous speaker. So let me say, what does it mean by power electronics? So I think in true sense, it is a technology associated with the conversion process. So you have one of the four possible choices here. You convert AC to DC, so-called rectification. You convert from DC to AC, so-called conversion. Then you have AC to AC conversion and DC to AC conversion. So you control the change and control the change of voltage current and AC. And the heart of the power electronics is obviously this true semiconductor process. So I will show you some packages which you have quite often seen in your research and development activities. This package well suited for the electronics. Something I should say 1000 volt or 2 kilovolt or less than that. Few amperes, 5 amperes, 10 amperes, up to 100 amperes. Then you have the other package, low pack, maybe for medium power applications. Then you have link pack. I brought here this link pack here, so you can see here. And then we have stack pack. You have seen this some of the, I think, model slides, HVDC product. So power electronics is more relevant today. You can see in all walks of the life. And then for power electronics solution, these should be adopted to the application needs. They are used for optimal and cost-effective operational outcome of the power systems. I think that you have seen some form of this slide by Ali Raza as well. So power electronics conversion process you can see in various stages during generation, transmission, and distribution phases. So you have on this side the generation part. You can have more traditional. Well, by the way, these all red parts mean that you have some form of conversion process, which is so-called the presence of power electronics during generation, grid, transmission, and industrial large-scale commercial distribution as well. So you can see more traditional generation, hydropower. Then you have wind, then you have pumped hydro, and then you have more solar panels or photovoltaics as well. Then you have hydrogen energy storage. So all these generation means you see the visibility of power electronics at various places. Then you go all the way down to grid. You have HVDC. Mauro has described very well, completely, I should say, the HVDC transmission networks. And then we have the distribution, industrial commercial scale distribution part here as well. So you can see here through the transport process. You have the water mobility, storage, application as well. So you see the importance of power electronics. Maybe you should use this. I think it's hard to do. Okay, sorry. Thank you very much. So you can see here the visibility of power electronics from generation, transmission, and distribution, the whole value chain of power systems. Well, drivers and why we are doing research in power electronics, I think the drivers and trends were shown by previous speakers, but I am presenting in somewhat in different ways. So you see the global trend of developing mega cities because the population growth is going on. Then you have human mobility is quite much from countryside to the cities. And right now we have, I think, almost 12, 13 cities in the world with a population of over 20 millions. You have something 20, 25 cities in the world with a population of over 5, 6 million. So this is one mega trend. Then you have faster electrification growth. Electrification growth has been very slow over a period of time. So you have, right now you have 8% of the world population by the end of 2030 still will have no access to electricity. So we must provide electricity to them. And out of those, 90% will be from the rural part of the world. So I think somehow 8% means that 870 or 74, I remember properly the number, million people, mostly located in South America, Africa, and Southeast Asia, they still don't access to the electricity. So that's one area that drive us to do some power electronics. Then you have the EV charging infrastructure here. This has been shown again previously. So this is again going on. More and more electric bikes become visible. You can see here some recent numbers. The end of electric bike sale by ICE, the combustion engines, internal combustion engine. Some manufacturers have already stopping and thinking to stop the production and adoption of EV electric bikes, and then you need a charging infrastructure for them. And then more and more renewable we are going to use. This is more country specific and site specific, but renewable energy will be more and more. So these drivers led us to a possible challenge here. So you need to produce energy sufficiently to meet the growing demand. It should be more efficient transport, and then we should use more and more renewable here as well, so as to limit the carbon footprint for secure, environmental friendly and affordable energy supply for you and for me. Well, we have world electricity demand by sector. So here you can see the electricity demand will be more than double between 2020 up to 2050 here, and mostly this doubling process is going on in residential, transport, and commercial prices. Then on the other side, the world grid connected electricity generation by different power station types. You can see here some conventional way of electricity generation by coal, oil, and gas. What they are declining here over a period of time, while the renewable part is gradually increasing here. You can see here by 2019, more or less 26% by renewable sources today, and they are going to be 82% in 2050. That's the very fresh number I just copied from the DNV report. So the basic unit in a power system is the power converter that you use in almost all power systems. So your power converter is the basic building block, and this slide is a bit old because it's earlier from the, if you see on this side, it's more ABB dominated products. If you see on this side, it's more Hitachi Energy dominated products. But these are all power converters products from earlier ABB and today Hitachi Energy, from few kilowatts to gigawatts. So we have a large portfolio of high power converter for different applications. You can think of EV charger here, few kilowatts for cars, buses, trucks. So you can charge them overnight, and then during the daytime you can have zero emission and you can drive. Then we have solar inverter for residential and commercial markets here. So you can see the solar inverters here. Then we used to have different drives for metallic industry, for plastic industry, for food and beverages, for oil and gas. So we had long list of drives here. Then we have the UPS system, wind turbines, medium voltage wind turbines, low voltage wind turbines, medium voltage wind converters. Then on this side we have more high power StatCom. I think Andrew was showing quite much about StatComs. And then we have also HVDC products as well. So to realize a power converter, I think it's kind of multidisciplinary research platform. So you should have a power semiconductor device knowledge, power semiconductor packages, power capacitors and inductors there. Then you have transformers, insulators, and thermal management, and electromagnetics. And not last but not least, you should have a
comprehensive knowledge about intelligent control methods, reliability and diagnostic, and internet type things. So it's multidisciplinary research platform, and you have with this knowledge in mind, then you can think of realizing power converter according to the customer specification, and of course according to the customer specification and customer satisfaction. Let me talk about the vertical value chain of power electronics. You start with a silicon chip or whatever silicon carbide chip here. You put several chips in parallel. We used to call sub-modules to increase the current rating. Each chip, let's say 50 ampere or 40 ampere or 30 ampere, depend. Then you put several chips in parallel to get high current rated sub-modules. Then you put several sub-modules in parallel to get a so-called power module. And this is our loving way we use today in HVDC application there. So you have collector on this side, bottom side is the emitter plate, and then you can see here is the gate connection there. So today these type of stack pack modules are visible in 4.5 kilovolt and even 5.2 kilovolt with current ranges of something 2 kiloampere and 3 kiloampere. Then you put two modules in series, upper side and lower side, to make, we used to call it converter cell. So you put these two guys here up and down, and then you have a capacitor across, and then you put gate drivers across each sub-modules to drive the current and turns on and off of semiconductors. So you put here the gate drivers here. Then you have several devices here in series all together with drivers each. You can make a cell here, and then you have several of these cells to make a converter arm here. You have some other environmental variables like fiber optics and cooling pipes to control the heat dissipation. And then you have several these cells in series here, and then you have three-phase converter here. So the whole wall hall looks like occupying some of football size, or maybe 20, 30, 50, 40 meters. So it's a very, very big product. This slide was, you have seen this HVDC product by Mauro Monge here. So we have two types of HVDC products, HVDC Lite, where we are using IGBT semiconductors here. This type of product might utilize LAN cable, overhead lines, or C cables. And this is a voltage source converter. Mauro has discussed quite much this one. Then we have also HVDC Classic here. There we use a thyristor-based semiconductor products. And there we have also we have quite much power in going up to the gigawatt here as well. So why we are talking about Hitachi Energy? We are talking about 60 years of HVDC experience and 120 projects worldwide, with 70% of all the VSC HVDC links in the world. So we are really a market leader, as Ali was saying. Well, okay, we have three semiconductors, namely silicon, silicon carbide, and gallium nitride. Now these three semiconductors are covering more or less 100% of the power market, I should say. I'm not talking about low power electronics, but I'm talking about high power electronics. So these are the three real leading house materials covering almost all power electronics here. So you have three semiconductors material, you have four semiconductor types. You have gallium nitride. Today these are existing low power range, something from 200 volt to 1200 volt, I should say roughly speaking, maybe even more, up to 650 volt. These are gallium nitride and HEMT devices. These are lateral devices, both available normally on and normally off. Well suited for very low power but very high switching frequency application. These are unipolar devices, means only one type of carrier is there to conduct current. Then you have MOSFET here. This is again a unipolar device, something a bit higher in power range. You can see here these MOSFETs are available both in silicon carbide, not for gallium nitride material. Then you have IGBTs here, IGCTs and thyristors. These are all bipolar products, means that there are two types of carriers that give you the current, meaning electrons and holes. So these devices, IGBTs, IGCTs and thyristors, are for very high power, but for very low switching frequency. Why? Because these electrons and holes. So you have bipolar devices. You have electrons which are lighter, moves fast. You have holes which are bulky and heavy. So it does take more time, transport time to turn on and off. So you cannot allow them to use for very high switching frequency application. And then on the power range, I put it here that for high power, these are well suited but very low frequency. On very low power, these unipolar devices are nearly ideal for very high frequency applications. So today, silicon is a more mature technology and leading horse in many demanding applications, low, medium, and high power range. Silicon carbide is expected to replace, and it has already started to replace, silicon in many low power applications. Voltage ranges, you have silicon carbide devices today from, I should say, up to maybe 1.2, 1.7 kilovolts are easily available. You can also get 3.3 kilovolt and 10 kilovolt based on some NDA with some commercial, few limited commercial suppliers. But on the literature, up to 2030, I will show later, 20, 30 kilovolt have been demonstrated in the scientific literature. Gallium nitride devices are quite much available, up to 650 volt, maybe up to 1.2 kilovolt, both normally on and normally off devices, well suited for medium power and with higher switching frequency. Some new device types like silicon carbide MOSFETs, the vertical GaN devices are emerging, but these are on very basic research level. There is no commercial GaN vertical device yet. So whatever you see today is the lateral lateral gallium nitride device. Well, Hitachi Energy Playground, if you see here, MOSFETs are low power. I plotted here in this dotted line, many vendors here, mostly up to maybe 600, 700, 800, 900 volt. Hitachi Energy Playground is something on very high power on this corner, upper right corner. You see high voltage and high current devices here. Then you have, I didn't show here in the GaN hand, there will be even more something in this corner. And then on the market side, Hitachi Energy is 1.2, 1.7 kilovolt and up to 6.5 kilovolt IGBTs. So you can see here the low power, medium power, and very high power semiconductor devices. But as you go up and up in power, so your market is shrinked, so your market goes down here, and we expect mean the HVDC effects maybe in 10 years time frame. Should be possible. It is possible to adopt silicon carbide devices in one of our future applications. They are not being used today, but these are good futuristic candidates we might think of. But in some application, at low power application, they are already being realized in some of the converters. Okay, some challenges in SiC power converter implementation. So since we are talking about silicon carbide, so we are talking about, yes, very lower losses, very fast switching application, very fast switching, shorter switching time. They gave us high blocking voltages here. They also are well suited for high junction temperatures here, and then it allows for better integration, power integration. But each benefit comes with some possible challenges here. So you want to have shorter switching time, but the question is how to design a system to handle high di by dV, di by dt, and dV by dt. How to handle you need to have high performance controllers there as well. You need faster protection and good shielding environment. And then since you are switching very fast with high dV by dt, you might expect stray capacitance current associated with some parts of the conductors here. And then you need to have better EMI filter design here as well, because you are switching very fast. So you might have some conducted and radiated EMI emission there as well. So high blocking voltage here. So the question is how to handle faults with high blocking voltage. And then if the insulation breaks down, what happens then? High junction temperature, so you have temperature compatibility with other components. Do you have the good temperature compatibility? Thermal fatigue issues here. And then you need to have SiC compatible components and converter systems, in our case especially the reactors, sensors, capacitors, transformers. So we need to check whether SiC is compatible to our existing power systems or not. So there are several technological gaps here. What the silicon carbide will react if you have several devices in series, for example. You need to have synchronized switching for for efficient conversion process here. So these technology gaps by SiC power converters must be closed before their implementation in the field. So then there are many reliability concerns here since we are considering to adopt silicon carbide, which is not mature enough yet. So you might think of that the overall reliability, and if you break down the overall reliability, you have the reliability coming at the wafer level, and there you have by default some defects coming from the SiC substrate, which is coming from the good or bad crystalline quality of the semiconductor. You have the second source of defects generation through epitaxial growth process, and then you have depend which growth technique you use to have an epitaxial structure here. Then you start manufacturing devices, so there are various unit process steps. You are adding more defects there through gate oxide formation, for example, ion implantation steps, and other junction termination extensions. So there are various process steps. It takes, I think, 2-3 months to get a device out of it. So each step, there is a probability of adding more defects. So more defects mean damaged chip, and damaged chip, of course, you cannot use. Then you have the module. You put several chips inside a power module to make and to realize a module. There you have die attach process here, bonding wires, sintering process, topping or passivation material, terminals and joints. So there are many reliability concerns coming out there. And then you have the operational reliability aspects. Depend your power module, which application and which switching environment you are going to use. You might have some issues with markups, bus bars. Then you have the switching patterns here, IDV by DT and DI by DT, thermal management, and where you are going to switch, meaning that how far away you are from the safe operating area, if you are closer to the safe operating area or not. So design for reliability at power and module level is prerequisite to system operational reliability and stability in the field. So the message here is this, that various reliability concerns during converter operation poses major threats to system performance. So from now onward, I will be more specific to the semiconductor itself. Well, what is the role of semiconductors here? You have 3 types of semiconductors, namely rectification. You have the diode here, and diode allows you to conduct current in one direction. There is no way to conduct current in other direction, so you have a single direction here. Then you have this other role, which is amplification here. So power semiconductors are used to amplify electric signals. You can see here some potential circuits, LNA, low noise amplifiers, power amplifiers, mixers, phase shifters, and attenuator circuits. And then the third one is the switching. Here you are using semiconductor as a switch. You close the switch, you get the light here in the bulb. So you are just apply the gate signal here, then you switch on, off, on, off, on, off. And these switches, you can see here one of the semiconductors I brought it down here. It's half bridge. You can use it for half bridge phase leg here. So these are the 3 these are the 3 roles of semiconductors: rectification, amplification, and switching. Now this is my favorite slide. So here I put all in one. You have all semiconductors existing today, whether it is low power, whether it is medium power, whether it is high power, whatever application. So you can see the existing of one of the material in different types of transistors. So I started with silicon because both low power and high power, I put it at the origin here. So you have a very cheap material, widely available on this planet. And then if you go in this direction, you have a low temperature, low power route. So I was trying my best to put all semiconductors in one slide. So you have low power, low temperature route in this side. So you can use this for consumer electronics, you can use for telecommunication, satellite communication, astronomy, whatever. So if you go in this direction, your frequency is increasing because superior transport properties of semiconductors here, but the cost is also increasing here in this direction. You might expect diodes, 2-terminal devices, MOSFETs, heterojunction bipolar transistors, and HEMTs or p-HEMTs. Chip size is normally used to be 1 millimeter, maybe less, something around in this range. If you go in this direction, so you have high power, high temperature route, and this is our Hitachi energy route here. So you start with silicon, currently widely available, all silicon devices from 1.2 or even from, let's say, low power to very high power, medium power, and very high power. Then you have GaN, gallium nitride, silicon carbide, and there's a new emergence of new material which is still far behind than that of silicon carbide, but it's popping up as well. Then you have diamond and aluminum nitride. Cost is extremely going up here, so you use one of these candidates commercially available, only gallium nitride, silicon carbide, and silicon for high temperature, high power, and fast switching applications. Now, what comes in your mind when you read this number? So I leave this question to all PhD students here. What do you think of these numbers? So you might have 30 seconds to think about this one. So I think the correct answer will have good acknowledgement from me. No, I didn't. No. Yes, I was here. So you have 300 fabs in the world. So you have 300 millimeter fabs, 121 fabs in the world of size 300 millimeter fab size, and then you have 200 millimeter fabs, something around 210. So this is really a growing market applications and supplying all types of chips worldwide. 13 10 to the power 21 means total number of transistors shipped so far since the invention of transistors from all fabs of the world. Doesn't matter you talk about low power, medium power, high power. These are total number of transistors shipped so far from all fabs of the world, worldwide. I'm talking about number which is far exceeding the amount of hair on a human body. I'm talking about a number which is more than the total number of stars in the radio galaxy. This is a very, very big number. I think the real numbers might be larger because this number is old, 2018. I'm expecting some big fresh numbers. Okay, for all power systems and power electronics application, whatever power electronics, you have the big fives here, namely the band gap, mobility, carrier mobility, thermal conductivity, dielectric constant, and carrier velocity. You can expect a potential outcome, good or bad, for all power application from these 5 fundamental material characteristics. These material characteristics ultimately defines the outcome of any power system. I took the values of these which are visible in the scientific literature, and I defined a 5 figure of merit here. These are a very popular figure of merit. We used to call Bezige's figure of merit, Bezige's high frequency figure of merit, Johnson figure of merit, and combined figure of merit, and then Keyes figure of merit. So all 5 figure of merit, I put these figure of merit here, and I normalize with respect to silicon. So you can see here the wide band gap are far exceeding several times, 10 times, 100 times, even 1,000 times, depend which figure of merit you take into account compared to existing silicon. So I think these are probably there are technological issues, cost issues. We don't have these devices from these materials, aluminum nitride, gallium oxide, and diamond. But silicon carbide and gallium nitride, you think the far superiority of these two materials compared to silicon. So silicon, which is widely available, cost is low, material quality is excellent. You have the growth process, oxide growth process here. Wafer size of 6 inch to 12 inch are visible. Power devices are available for very low power, up to 6.5 kilowatt. And technological readiness level you have is quite mature technology, 50 years of experience there. Technology development experience, so you say technological readiness level is 9. Then you have silicon carbide here. Silicon carbide stays at the market entry at the doorstep of the market. You have cost which I would say low to medium. I will later show the actual numbers here. You have material quality, which is, I should say, still the medium. Oxide growth is possible, yes. You have wafer size today 4 inch, 6 inch, 8 inch. Power devices are available up to 1.7 kilowatt, even 3.3 kilowatt as well. We just advertised from Hitachi Energy 3.3 kilowatt. Lean pack devices, technological readiness level, to my understanding, stays something 7 to 8. Gallium nitride follows the same pattern. The cost is better because you have cost which is low to medium, because lower than equivalent silicon carbide, but slightly higher than equivalent silicon here. So Mostly gallium nitride is available on silicon, but other commercial products are also available on other substrates, silicon carbide. Gallium nitride don't have their own substrate, so it's kind of alien material on gallium, silicon or silicon carbide. Power devices from 0.2 to 1.2 kilovolt technology readiness level is quite mature. Gallium oxide, they are just starting to appear here. So you have wafer size of 2 to 3 inch. It's very expensive material. I should say it is lacking something 10 years it's behind than the equivalent silicon carbide here. Oxide growth, we haven't seen this yet. Wafer size 2 to 3 inch, power devices, commercial power devices, no. Technological readiness level is, I think, is very, very low. Still, it takes into account the basic university level research. Then you have diamond material here, very, very expensive. Material quality is poor. There are many technological development steps there. Wafer size is 1 inch or maybe 2 inch maximum. I don't think more than that. Power devices, no. And then we have the aluminum nitride material. Cost is very high. Material quality is poor. Oxide growth not. So I just try to put some pros and cons of different materials, a kind of potential candidates for power applications here. So what should we expect from the wide band gap devices here? So I try to calculate some parameters here. Drift layer thickness, which is more fundamental parameter than the design of the semiconductor device. So silicon, as a function of drift layer, I plotted as a function of the blocking voltage here. Assuming for 20 kilovolts, you have 1000 micrometer thick. Assuming 1000 micrometer thick drift layer. Today, 6.5 kilovolt IGBT, by the way, we are using 680 micrometer for silicon IGBT in our products. So assuming it is silicon carbide, so we only use to 6.5 kilovolt means 60 micrometer, something around. So it's 10 times less. And this is theoretically is also, you can see here, for 20 kilovolt. So you have drift layer thicknesses which much thinner for wide band gap than equivalent silicon. And then you have the OR-on resistance comes the same way. So you have OR-on here for 20 kilovolt, you have several order of magnitude lower OR-on for wide band gap devices than equivalent silicon. And then I try to plot the blocking voltages assuming the same drift layer. These are just theoretical calculations. And I plotted I plotted the blocking voltage and normalized with respect to silicon here. So assuming silicon is 1, so you might expect several times higher blocking voltage for wide band gap devices, even much higher for aluminum nitride devices. But of course, there are some technological challenges and issues there. So all in all, the messages here is this: you might expect a thinner chip using wide band gap. You might expect lower OR-on. You might expect higher breakdown voltages. So roughly speaking, OR-on is something less than 10 times than silicon. Drift layer thickness is roughly 10 times than silicon. And blocking voltage depending on the design of the epitaxial layer. So you have several times much better blocking voltage than equivalent silicon. So how the physical layer structure of semiconductor look like? So you have today in all commercial products, you have the planar MOSFETs here. You can see here the gate terminals, source terminal, and since it is a vertical device, the drain terminal is sitting on the back side of the substrate. So you can see here the oxide here is because it's MOSFET. So metal is some insulation material oxide which is sandwiched between the semiconductor and the metal. And then if you see here the semiconductor layer structure, so different parts of the semiconductor contributes in the on resistance. So the total on resistance is sum of on resistance, total on resistance is sum of contact resistance, which is the semiconductor metal contacts, channel resistance, which means the top layer where you start the transport process starts here. Then you have the JFET part, which is here, and then you have the major part, the drift part here. So, and then you have the resistance of the substrate here. So there are various compositions of the on resistance here. Let's take it more. You can see here the contact resistance approximately remains constant for different blocking voltages here. Substrate resistance, let's say approximately remains constant. This is just the analytical understanding, not the actual numbers. And then you see here, if you go to higher and higher voltages here, so your drift part becomes more and more dominant here. The lower voltages, maybe the channel resistance is more dominant, but for higher voltages, you have more drift part which becomes the dominant which takes the dominant contribution in the total on resistance. And on total on resistance is the main parameter that affects the switching performance of the devices here. So power semiconductor chip with lower on always guarantees lower losses of power converters. So then you have the trench, other design here, where you see the vertical trench here, shaped the gate terminal, which is gate metal is sandwiched here in vertical directions. You have the oxide here, and your transport is going all the way down. Then you have the IGBTs. So IGBTs is a bipolar device, contrary to unipolar devices. If you look the MOSFETs on the top side, you have, if you look the IGBTs on the top side, you have MOSFET type structure. If you look on the bottom side, you have BJTs, bipolar junction transistors. So it's IGBT is sum of two MOSFETs plus BJTs. And then you can see here the top view, whether it is IGBTs or whether it is MOSFET. You can see here the top view of a semiconductor chip. You have the source pad there, you have the gate terminal, and bottom side you have the drain terminal or the collector terminal of the device. Then you have this what is called light red area here, so-called edge termination area. You need to suppress and you need to control the electric field at the outer surface of the chip. This is not the part of the active area. So here you have the passivation, you have edge termination structure, and you need to passivate here to contain and control the electric field here. So the active part of the device is this one, which is used to conduct the current. So silicon carbide, we used to say well suited for high temperature application here. So silicon carbide, you can see here, people have realized I just put few devices here at very high temperatures. All these are low power electronics application specific circuits here, JFETs, MOSFETs, then you have the SiC MOS gate drive circuit here, and then we have, I think, some Bellman is sitting here already, so some state of the art by that time. Circuits have been realized by Hot SiC project and Venus project, I should say, at KTH here. So SiC devices are well suited for exploring high temperature universe here. If you are going to consider, if you are going to Venus or Moon, I think silicon carbide is nearly ideal. There are many other applications, oil well drilling application here, and automotive sector here. There you have very high temperature, and I think silicon carbide provides good opportunity to exploit for some specific applications. As I said, high oil and well drilling, Venus explorations or moon exploration, because on the moon surface you have 180 plus and 180 minus during the day, during the full 24 hours, your temperature circulates. Then today silicon carbide has been demonstrated in the scientific literature. These are some state-of-the-art papers here. 1 kilovolt silicon carbide BJTs, you have the thyristors here, 20 kilovolts here, then you have 27 kilovolt IGBTs. They are not commercial devices. These are just have been demonstrated by different universities, and these devices are visible in the scientific literature. And then you have ultra high voltage SiC pin diodes here by Japanese group. And then recently, I think the people have shown super junction MOSFET as well. So ultra high voltage silicon carbide devices offer greater opportunity to secure high power technology development landscape. So that's the key message here in the state of the art SiC device technology. If you see the historical here, while silicon is still evolving, you can see the historical development of silicon starting from earlier 1950s time. You have BJTs, MOSFETs, IGBTs, GTOs, and so on and so forth. But they are still evolving. So some process steps, for example, which needs attention here. We are working in Lenzburg here in part of Hitachi Energy, advanced trench for high voltage integration concepts, try to increase the high junction temperature there, and some overloadability and SOA optimization processes going on. So silicon is still evolving. On the other side, silicon carbide is fast growing. We have silicon carbide, gallium nitride, widely here 0.65, 1.7 kilovolt MOSFET. Then we have silicon carbide, 3.3 kilovolt MOSFETs. Then you have silicon carbide, 6.5 kilovolts. And then we have just silicon carbide. There is no semiconductor transistors, commercial transistors beyond with silicon IGBTs. So there is no commercial transistor of IGBTs type or more than 6.5 kilovolts. So then you have three possible candidates here. You have bipolar IGBTs, maybe after beyond 10 kilovolts. Then you have GTOs, thyristors, bipolars, and then you have super junctions, unipolars, more than 10 kilovolts. So each has pros and cons. You might have ultra high voltage, higher V-on and medium switching frequency for IGBTs here, lower or-on, well suited for ultra high voltage, lower switching frequency. But then you have the super junction MOSFET for very high switching frequency application, ultra high voltage devices. So while more matured silicon power devices are still evolving, SiC devices are fast growing in the power market. Yeah, over here. So in Hitachi Energy, we have these candidates for diverse range of power application, namely for low power, I should say, for rail and e-mobility. We introduced a new device, silicon carbide road pack here. Then we have lin pack, as I have shown to you. It's just on the table here. We have both silicon and silicon carbide with 3.3 kilovolt and 1.7 kilovolt. We just advertised silicon carbide 3.3 kilovolt. I will show some results on the incoming slides here. Then we have thyristors. Then we have high pack devices with voltage class from 1.7 kilovolt to 6.5 kilovolts. These are IGBT devices here. We used to call high pack industrial power modules here, well suited for diverse range of power application here. And then we have stack pack, an ideal candidate for HVDC here. For the low power, I should say, or medium power, we have low pack and 62 pack devices here. We have IGCTs here, and then we have thyristors here. So a high quality power package is a central key to secure power electronics conversion process. When it comes to the power package here, so you might think of putting silicon or silicon carbide die here, then you have solder material here, and then you have a long list of different layers here. We used to call DBC, directly bonded coppers here. So you have copper, then you have the insulation here in between, then you have the copper, then you put the solder here, and then you have the base plate. So then you have the thermal interface material, and then finally you have the heat sink. So source of heat is your semiconductor die, and this heat is going all the way down, and then it's dissipating in the surrounding environment. You have two types of packages in the power market. One with base plate, which means this one, and one without base plate, which means this one. So this means that the base plate is not part of this one. So you have just DBC, and then you have directly the chip. So each has pros and cons. So some some material parameter that plays a central role in optimizing the package design, that you need to dissipate heat quickly and efficiently. This means that all materials should have good thermal coefficient expansion, well matched. You need high thermal conductivity here. You need high Young's modulus. And then you have the electrical conductivity as well. Melting point should be high enough. You have adhesion with the surrounding or underneath material, and process temperature of during the whole package design should be compatible to each other. So the ideal parameter for a module point of view is you are expecting ideally zero stray inductance and zero thermal resistance from junction to the case, and highest possible field tolerance under continuous pressure. In reality, this is lin pack, which we have 10 nanohenry and 31 Kelvin per kilowatt, and this easy pack product, this is I think something 7-8 nanohenry and bit lesser thermal conductivity as well. So what are the key performance parameters? What we are expecting from the high current packages here? You need high power density here. We need to expect lower losses. We are expecting higher SOA. We are expecting higher TJ as well. And then excellent ruggedness from the point of view of surge current capability, short circuit capability. It should have the low leakage current, and it should have the stable blocking voltage and lower fit rates, failure in times. Currently, silicon carbide modules, because of the material quality and yield and other different issues, our chip size is much smaller. I think in commercial products, probably 5-6
7 millimeter, not more than that. So for high current power module to realize, we need a larger chip size. So you can increase the chip area, or you need to put more chips in parallel. But putting more chips in parallel, you have a penalty that it might introduce some packaging complexity, junction termination extension for high voltage chips, and you might have some current unbalance. That means that you induce different type of stress in different chips. Currently available silicon module, we have low pack in this current range, thin pack in this current range, and so on and so forth. Silicon carbide is not available yet to offer you these high current rated modules. Mostly they are something 500 ampere or less. So I try to compare apple to apple. You have silicon carbide here, or new products, 500 ampere, 3.3 kilovolt. Then you have silicon 450 ampere, 3.3 kilovolt. This is our double pulse test setup here. Both modules were tested in the same test environment. You can see here the advantages of silicon carbide. Look at the slopes here during turn-off process, and here you can see it's very sharp. So your slope is very high. Same applies to the current here. So the blue part, which is the turn-off current here, and red part is the collector emitter voltage here, and here is the drain to source voltage here.
Okay.
And you can see here the difference of the turn-off losses here. There's a big difference here. Then you have see the turn-on process here. You can see here this is the diode, which is this one. So you can see here the reverse recovery loss is big here, 383 millijoules, while silicon carbide, you don't have the reverse recovery. It's very negligibly small value here. So you can turn on and off very fast. So the difference of the turn on and turn off losses comparing silicon carbide and silicon, you can see here is 7 to 10 times lower losses you get from silicon carbide. Now, putting all three materials together, one figure of merit to investigate the basic technological output is just multiply the OR on with the total charge of the total gate charge. And some Infineon guys have shown a comparative assessment of different devices, silicon superjunction. Then they compared it with silicon carbide, trench MOS and DMOS devices here. And gallium nitride, you can see here, is outperforming whatever figure of merit you take. So you can see here, for example, 320, while silicon carbide, you have much larger. So they have tried to show that gallium nitride outperformed than other competing technologies in low power application. Then what I did here is this: I took the commercial devices and took their data sheets here and tried to compare from different vendors here with more or less similar current rating and similar voltage. So 650 volt gallium nitride versus silicon carbide. And then you can see here 1.2 kilovolt gallium nitride versus 1.2 kilovolt silicon carbide. Remember, gallium nitride is a lateral emitter device. So this proves that gallium nitride for very low voltage application probably is better choice than equivalent silicon carbide. Sorry to say that, but it is the truth. So I think I just close like that. So you can see the historical development here. I try to put the historical development, the silicon wafer size here, an evolution process here, and I think the green curve, which is the silicon carbide power, it's following the same pattern here. And then you have the silicon carbide here, silicon low power here, and silicon high power, different wafer sizes. So evolution process is approximately linearly over the period of time. Gallium nitride or gallium oxide, aluminum nitride or bulk gallium nitride, gallium oxide, they are still at 2 inch or 1 inch. The price wise, some old numbers, you can see here 7 to 8 times more gallium nitride, aluminum nitride devices than equivalent gallium nitride on silicon. This is just the epi and the wafer cost. It's not the full device cost, but it's clear that silicon carbide devices are far expensive than equivalent silicon. What I did here is this: I took from the DigiKey some numbers from different vendors here. These, I think, the Cree squares are from ROM, and similarly Infineon and onsemi, so on and so forth. So I normalize these numbers with respect to equivalent silicon half bridge 62 packs here, and mostly I think my numbers were staying somewhere here. So you have 2 to 4 times, I should say, depending on the current rating. Your power modules are available for silicon carbide. This is the number from the Digi key. So the price wise, I think it's still 2 to 4 times than equivalent silicon here. So the message is here is this: the silicon carbide power module present higher cost, but wafer size has evolved rapidly over a period of time. But you might expect the overall system performance, based on the overall system performance, probably your silicon carbide will not be so costly as we used to see here on this slide. Now, silicon carbide, the cost breakdown driver here. One of the breakdown driver is the surface defects and the yield. If you have 30 micrometer thickness here and 6 inch and 4 inch epitaxial growth here, assuming the defect density is the same, and for 100 micrometer 4 inch wafer, you have a lot of defects here. So you have the defect density which is much higher, and the chip yield is strongly depending on chip area and how many chips you have on the device surface. So more chips you have, lower the device yield will it be, and this means cost. So the overall cost is a function of yield, epitaxial thickness, wafer size, production volume, and competition. More and more vendors becomes available, and the confidence level of the end user will be better and better. You might expect lower cost here. Total number of defects is a sum of substrate defects, epitaxy defect, and manufacturing defects. These defects must go down so as to realize large area silicon carbide device. On the market point of view, you see here the growing confidence level. Some recent numbers shown by Yole 2-3 years before. I think maybe it still is applicable. Gallium nitride and silicon carbide. There is no new market. So silicon carbide and gallium nitride is capturing the existing silicon power market. So you can see here, silicon carbide is taking more and more market share here. When it comes to the market share by voltage class, mostly the market is low voltage dominated. Then you go to medium voltage, then you go to higher voltage. I think this kind of reflection was visible in my earlier slide in this presentation, that higher voltages here, you have the less market volume. Then on the market by different application types, the dominant applications stay at the automotive sector here, as you can see here, and with the cumulative annual growth rate of 34%, I think they are reaching something $6.2 billion. We recently have an industrial PhD student, Daniel Johansson. He has finished his PhD. I think I should say this is state-of-the-art silicon carbide. We didn't realize this, but it's TCAD realized devices here. We calibrated the model here, 22 kilovolt, IGBTs here, pin diodes here, and once the model was calibrated, we evaluated different IGBTs and thyristor with ultra-high voltage capability. We went up to 50 kilovolt here. You can see, well, this one was especially silicon carbide MOSFET 10 kilovolt. We got from, under some agreement, we got from one vendor here. So we realized this in our half-bridge circuits here and try to test it both static-wise and dynamic wise, the capability of silicon carbide MOSFETs here. And this one you can see here 4 or 5 times more short circuit current and short circuit duration of something 3 microseconds. This is my last slide. I think silicon power devices are fairly matured but still evolving for high power application. Silicon carbide opens up a lot of possibilities for system improvement in terms of cost, size and performance. Full potential of SiC is revealed for high switching frequency application. Currently SiC is strengthening the confidence level for low voltage application. Still there remains challenges for SiC before large scale implementation in power converter. You can see a visionary landscape of adopting and silicon carbide. Thank you very much.
We're slightly running out of schedule, but we have time for 2 questions.
Thank you so much, Kumar, for the nice presentation. I have a couple of questions. The first one is related to your, you have shown in your slide that the diamond and the as well as the on-state resistance as compared to the gallium nitride and silicon carbide. And in one of the slides you have shown the figure of merits, 5-figure merits, and you have shown that the diamond and the aluminum nitride and the gallium oxide has higher figure of merits as compared to the silicon or silicon carbide. Then why we are not designing the power devices from these materials?
There are many technological issues there because diamond is hot material. You have aging issues, you have growing issues. So that's the reason that you don't have P-type, for example, materials available for diamonds and for aluminum nitride. So there are many technological issues, and of course cost is there as well. I mean, you have technological issues, for example, ion implantation steps, patterning this diamond material. You have to age, you have to deposit. So these are the typical, I should say, the technological issues. Yeah, Ben.
Yeah, maybe I can comment. You said here that gallium oxide doesn't have a MOS oxide. It is only MOS oxide. It is in lack of a semiconductor. Gallium oxide does not exist as a semiconductor. There's no P-type.
Gallium oxide doesn't have P-type either.
I don't think it will ever become a power device.
Even one other disadvantage for gallium oxide, if you can see here, it is very, very poor thermal conductor. Thermal conductivity of this material is worse than all other semiconductors. And that is the bigger question for all type of power application, because you cannot dissipate heat which is generated by some parts of the semiconductor device.
I want to point out one mistake in slide 18.
Yeah,
No,
I think this is 18, huh? Here?
it's
17.
1990.
Here.
So the figure of ohm resistance is correct, but then you say that ohm resistance of silicon carbide is a factor of 10 of silicon. It's more like 200 to 400 times lower. Ohm
Yes.
resistance.
Yes, it's just an analytical understanding. It's not the actual number that you're presenting here. You're right.
You say R on silicon carbide is R on silicon divided by 10.
Yes,
It should be 100 or 200.
yes, here.
The drift layer is 1/10.
Yes, or on, you can see here some, okay, it's not exact, but I just was roughly presenting the numbers here.
Roughly, yes, but the big reason why silicon carbide is commercial today is 200 to 400 times lower ohm resistance. Not 10. So your figure shows the correct thing, but I think the text should reflect.
Okay, thank you.
There's some collaboration needed here. Let's
I think it's just a mistyping. You got the correct one.
Okay,
I think.
but if you see here numbers, for example, you agree with these numbers, huh?
Yeah,
Yeah.
but the text.
Yeah, I understand. It's quite okay.
I see there's a lot of questions.
Yeah.
I know Hans has to present, but maybe we can shorten our presentations, Hans, you and I.
Yeah, but I can make it very short. Or I can
So what do we do? Okay, one question. Let's see who has.
We know what you're going to say.
Go ahead. One. Yeah, please. Yes.
Thank you very much for this very, very interesting overview. You mentioned this high temperature devices, but I assume that you also work on devices for radiation harm
Yes.
electrons for low gas.
Sorry.
Yeah,
What are you seeing? Okay, sorry.
it's okay.
It's okay.
Yeah. I think there is a lot of information about the radiation hardness level of silicon carbide with respect to silicon. I would say it's better, I should say, roughly speaking. It's better than